Welcome! In this session, we'll explore LeetCode problem number 1455, check if a word occurs as a prefix of any word in a sentence. This problem focuses on string manipulation and prefix matching, an important concept in many coding scenarios. Let's dive in and break it down step by step. In this problem, you are given a sentence that consists of words separated by spaces, and a search word that is a string. The goal is to determine whether the search word appears as a prefix in any of the words within the sentence. If it does, we need to return the one-based index of the first word where it is a prefix. If it does not appear as a prefix in any word, we return -1. A prefix of a string is essentially a substring that starts at the very beginning of that string. For example, in the word apple, AP is a prefix, but PL is not. The input consists of two components, the sentence, which is a string of words separated by spaces, and the search word, which is another string. The output is an integer, which represents the one-based index of the word where the prefix matches, or -1 if there is no match. Let's look at an example to make this clearer. We are given the sentence I love eating burgers and the search word burg. The words in the sentence are split into a list as follows: I love eating burgers. Now, we check each word to see if it starts with burg. The word burgers, which is the fourth word in the list, starts with the prefix burg. Since it matches, the output is 4, representing the one-based index of this word in the sentence. In another example, the sentence is "This problem is an easy problem" and the search word is pro. Breaking the sentence into words gives us, "This problem is an easy problem." We check each word to see if it starts with the prefix pro. The word problem, which is the second word in the list, starts with pro. Therefore, the output is 2 because we return the one-based index of the first matching word. Now, consider the sentence I am tired with the search word you. Here, the sentence consists of the words, I am tired. None of these words start with the prefix you. Since there are no matches, the output is -1. Finally, let's discuss the constraints and edge cases. The sentence will always have a length between 1 and 100 characters, with words separated by single spaces, and the search word will be between 1 and 10 characters long. Both the sentence and search word will only contain lowercase English letters. In edge cases, if search word is longer than any word in the sentence, the output will be -1. If search word matches multiple words, we return the index of the first match. If the sentence has only one word, the output depends on whether that word starts with the search word. To solve LeetCode problem number 1455, we need to determine if a given search word appears as a prefix in any word within a sentence. One straightforward way to approach this is through a brute force method. Here, the intuition is simple. We iterate through each word in the sentence and check if the search word matches the prefix of the word. This can be achieved using Python string slicing or the built-in starts with method. The steps are as follows. First, split the sentence into an array of words using the split function. Then, go through each word and check if the search word is its prefix. If a match is found, we return the one-based index of that word. If no match exists, we return -1. In terms of complexity, the time complexity is O, n * k, where n is the number of words and k is the average length of the words. The space complexity is O, n, as we need to store the words after splitting the sentence. The brute force approach is simple and easy to implement, but it has some potential drawbacks. It may perform unnecessary computations, especially when there are many words in the sentence, and a match is found early. To address this, we can consider an optimized approach that utilizes early termination. This method still involves splitting the sentence into words and checking prefixes, but it focuses on stopping the iteration as soon as we find the first match. The steps include splitting the sentence, iterating through the words, and using starts with to check for the prefix. Once a match is found, we immediately return the index. If no match exists, we return -1. In terms of complexity, the time complexity remains O, n * k, but the loop may terminate early if a match is found. The space complexity is still O, n, due to the array of words created during splitting. The optimized approach is more efficient when a match occurs early, but it still requires splitting the sentence, which uses additional space. To save space, we can explore an alternative approach using a two-pointer simulation. This method avoids splitting the sentence into words and instead processes the sentence directly using pointers. 2 pointers help identify words as we traverse the sentence, checking if the search word matches the prefix of the current word. A counter keeps track of the word index, and we return the index as soon as a match is found. If no match exists, we return -1. This approach has a time complexity of n*k, where n is the sentence length and k is the average word length. However, its space complexity is 1, as no additional space is required for storing words. The 2-pointer simulation saves space by avoiding the creation of a word array, but it comes with its own trade-offs. The implementation is more complex and prone to errors compared to the other methods. For this reason, we chose the optimized approach with early exit as our preferred strategy. This approach strikes a balance between simplicity and efficiency. By leveraging Python's built-in split and starts with methods, we can keep the code both readable and concise, while ensuring good performance for most cases. Although the 2-pointer approach uses less space, the minor savings do not outweigh the increased implementation complexity. Some key observations that influenced this decision include the simplicity of prefix checking with starts with, the efficiency gained through early termination, and the practical trade-off between space and complexity, which often favors readability. The chosen strategy provides a balanced and practical solution for the problem. It ensures readable and concise code while remaining efficient for real-world inputs, where matches are typically found early in the sentence. The time and space complexity trade-offs are minimal, and Python's built-in methods make the implementation straightforward. By combining early termination with efficient string operations, this approach addresses the problem effectively without unnecessary overhead. Overall, it provides a solid and well-rounded solution for handling prefix checks in a sentence. To solve this problem, we start by understanding the task. Given a sentence consisting of space-separated words and a search word, we need to determine if the search word is a prefix of any word in the sentence. If we find a match, we return the 1-based index of the first matching word. Otherwise, we return -1. First, we parse the input sentence by splitting it into a list of words using Python's split function. This gives us an array of individual words to process. For example, if the sentence is "this is a test," splitting it results in the list "this is a test." Next, we iterate through this list of words using a for loop, while keeping track of each word's 1-based index using Python's enumerate function with the start parameter set to 1. For instance, with the list "this is a test," the loop will provide pairs like 1, this, 2, is, and so on. For each word, we check if it starts with the given search word using Python's starts with method, which is both efficient and easy to use for prefix matching. For example, if the search word is te and the current word is test, the starts with method will return true, indicating a prefix match. The moment we find such a match, we return the current 1-based index of that word. However, if we finish iterating through all the words without finding any matches, we return -1, signaling that no word in the sentence starts with the given search word. Now, let's consider some edge cases to ensure our algorithm handles all scenarios. If the sentence is empty, there are no words to check, so we immediately return -1. When the search word is an empty string, every word in the sentence will technically start with it, so the correct output is 1, the index of the first word. Additionally, if the search word is longer than all the words in the sentence, no match is possible, so the output remains -1. By leveraging Python's built-in starts with method, we avoid manually iterating through characters for prefix checks, making the solution both concise and efficient. Using enumerate with a start index of 1 simplifies the handling of 1-based indexing, and the algorithm's short-circuit logic ensures that we stop processing as soon as we find a match. In terms of data structures, this algorithm primarily uses a list to store the words obtained by splitting the sentence. This list allows for straightforward iteration and indexing. For prefix matching, the starts with method is used, which is specifically designed for efficient string comparisons. Now, let's analyze the time and space complexity. The time complexity is n*m, where n is the number of words in the sentence, and m is the average length of the words. The starts with method only compares up to the length of the search word, so it operates on a subset of m characters for each word. On the other hand, the space complexity is n, as we store the list of words obtained from splitting the sentence.
Finally, here's the Python implementation of the algorithm.
We define a function as _prefix _of word that takes a sentence and a search word as inputs. The sentence is split into words using the split method. We then iterate through the list of words using enumerate, starting the index at 1. For each word, we check if it starts with the search word using starts with.
If a match is found, we return the current index.
If no match is found after the loop, we return -1.
Let's walk through an example to see the algorithm in action. Suppose the input is a sentence, this is a test, and a search word te.
First, we split the sentence into words, resulting in the list, this is a test.
Next, we iterate through this list. At index 1, the current word is this, and this dot starts with te, evaluates to false. At index 2, the word is, and is dot starts with te, is also false. At index 3, the word is a, and a dot starts with te, is again false. Finally, at index 4, the word is test, and test dot starts with t, evaluates to true. At this point, we return the index 4 as the output. This example highlights the efficiency of the algorithm's early exit mechanism, where we stop processing as soon as a match is found. Additionally, the algorithm handles edge cases like empty strings, mismatched cases, and non-matching prefixes, ensuring that it is both robust and reliable. Now, let's look at some specific edge case examples. First, consider an empty sentence with a search word of a. Since there are no words to check, the algorithm immediately returns -1.
In another case, if the sentence is apple banana and the search word is an empty string, the algorithm will return 1. This is because every word in the sentence starts with an empty string, and the first word's index is 1.
Lastly, consider a scenario where there is no match, such as a sentence hello world and a search word of hi.
Here, none of the words in the sentence start with hi, so the algorithm correctly returns -1. These examples demonstrate how the solution handles a wide range of inputs effectively, ensuring correctness in all possible scenarios. This Python implementation solves LeetCode problem number 1455, which checks if a given search word occurs as a prefix of any word in a sentence. Let's break it down step by step. The function is prefix of word takes two inputs, sentence, which is a string containing space-separated words, and search word, the string defined as a prefix. First, we use the split method on the sentence, which breaks it into a list of words. This allows us to process each word individually. For example, if the sentence is I love LeetCode, the split method returns the list I love LeetCode. Next, we use a for loop to iterate over the words in the list. The enumerate function is used to get both the index and the word at the same time. The index starts from 0, but since the problem requires a 1-based index, we add 1 to the index when returning the result. Inside the loop, we use the starts with method to check if the current word begins with the search word. If it does, we immediately return the 1-based index of the word. If the loop completes without finding a match, it means no word in the sentence has search word as a prefix, so we return -1. This solution is efficient and runs in O(n), where n is the total number of characters in the sentence, because we process each word and check the prefix in linear time. It also handles edge cases like an empty sentence or search word that is longer than any word in the sentence. This is the Java implementation of LeetCode problem number 1455, which checks if a word occurs as a prefix of any word in a sentence. The logic mirrors the Python solution, with differences such as explicit type declarations, Java's string split method for tokenization, and a for loop with an index for iteration. It returns the 1-based index of the first word matching the prefix or -1 if no match is found. To solve this problem, we start with a simple example where the sentence is hello world and the search word is war. First, we split the sentence into individual words using the split function. This gives us the list, hello world. Next, we iterate through each word in this list while keeping track of its index. In the first iteration, the current word is hello. We check if hello starts with the search word war, and the result is false since hello does not begin with war. In the second iteration, the current word is world. This time, when we check if world starts with war, the result is true because world indeed begins with war. Once we find a match, we return the corresponding 1-based position of the match.
Since the match occurred at index 1 in the zero base list, we return index plus 1, which equals 2. The final output for this example is therefore 2. Now, let's consider another example where the sentence is "this is a test" and the search word is not. Again, our first step is to split the sentence into words, resulting in the list "this is a test." At this point, we're ready to iterate through each word to check for a match. As we iterate through the words in the sentence "this is a test," we start with the first word, "this." Checking if this starts with not yields false. The same happens for the second word, "is," which also does not start with not. We continue to the third word, and again find that it does not match. Finally, the fourth word, "test," is checked, and it also does not start with not. After iterating through all the words, no match has been found. When this happens, the convention is to return -1 to indicate that the search word does not occur as a prefix in any of the words. Hence, the final output for this example is -1. Lastly, let's look at the example where the sentence is searching for a prefix and the search word is search. Splitting the sentence gives us the list searching for a prefix. During the iteration, the first word, searching, is checked to see if it starts with search. This check evaluates to true since the word searching does indeed begin with search. As a result, we immediately return the position of this match in 1-based indexing. Since the match is found at index 0 in the zero base list, we return index plus 1, which equals 1. The final output for this example is therefore 1. To analyze the time complexity of this solution, we start with the sentence.split function. This operation splits the input string into a list of words based on whitespace. Since the split function processes the entire sentence character by character, it takes n time, where n is the number of characters in the sentence. After splitting, we iterate through the resulting list of words. Let's call the number of words k. For each word, we use the word.starts-with search word method to check if the search word is a prefix. This comparison involves checking up to m characters, where m is the length of search word. In the worst-case scenario, this operation takes m time for each word, and iterating through all k words results in a total of k*m time. Now, because the number of words k is proportional to the total number of characters n in the sentence, and m is independent of n, we combine these terms. The overall time complexity simplifies to n, as the term k*m is linear with respect to n and doesn't dominate the analysis. Now, let's look at the space complexity. The split function produces a list of words, where each word is essentially a substring of the original sentence. If there are k words in the sentence, the space required to store this list is proportional to the total number of characters in the sentence, which is n. Aside from this, the solution uses a few temporary variables such as words, index, and word. These variables occupy a constant amount of space, which is 1. When we combine these factors, the dominant space requirement comes from storing the list of words. Consequently, the overall space complexity is determined to be n. Let's compare this approach with a naive or brute force method. A naive approach would involve manually iterating through each character of the sentence, identifying word boundaries, and checking prefixes character by character. This would still result in n time complexity for parsing the sentence and k*m for prefix checks, leading to a similar overall complexity of n. However, using Python's built-in split and starts with functions is more efficient in practice due to their optimized implementation. Now, considering the best, average, and worst cases, in the best-case scenario, the search word matches the prefix of the very first word. This allows the loop to exit early, resulting in a time complexity of n plus m. In the average case, the search word matches a prefix somewhere in the middle of the sentence. On average, about half of the words are checked, which simplifies to n time complexity. Finally, in the worst case, no word matches the search word, and all words need to be processed. Here, the time complexity is n, as every word in the sentence must be checked. To mathematically summarize the complexity, the time complexity involves two main components. First, splitting the sentence takes n time. Second, iterating over k words, where each word requires m for the prefix check, contributes k*m. Since k scales with n and m is independent of n, the total complexity is dominated by O, N. For space complexity, the primary space usage comes from storing the list of words, which is O, N, while the auxiliary space for temporary variables is O, 1. Combining these, the overall space complexity is dominated by O, N. This analysis confirms that the solution is efficient in both time and space aspects, leveraging Python's built-in functions to achieve optimal performance. When tackling this problem, it's important to avoid some common mistakes that can lead to incorrect results or inefficiencies. First, applying the starts with method directly to the entire sentence instead of individual words is a common error. This approach checks if the search word is a prefix of the entire sentence, rather than each word, which diverges from the problem's requirements. To address this, ensure you split the sentence into words using .split, and process each word individually. Another frequent oversight is ignoring edge cases such as empty strings or invalid inputs. For example, if search word is empty or the sentence itself is empty, the solution might either break or give unintended outputs. A good practice is to validate inputs upfront and return -1 right away for invalid cases. Additionally, watch out for inefficient string operations inside loops. Repeated slicing or concatenation can add significant overhead, especially with longer sentences. Instead, leverage optimized methods like Python starts with to check prefixes directly. Lastly, don't forget that the problem requires returning a 1-based index. Many programmers accidentally return the 0-based index, which is common in Python, so make sure to add 1 before returning the result to match the requirements precisely. Another potential pitfall is overlooking punctuation and special characters in the sentence. These can disrupt your logic by causing false positives or negatives if they aren't properly handled. The best approach is to ensure the problem constraints are clear about whether only alphanumeric words are allowed and to pre-process the input accordingly if needed. From an interview perspective, this problem highlights the importance of breaking the sentence into individual words and efficiently checking each one. The starts with method in Python is particularly handy, but you should also be prepared to implement this logic manually if using a language without such utilities. The problem is a classic example of substring and prefix searching, which is a common pattern in string manipulation tasks. Interviewers may also be interested in the efficiency of your approach. A good explanation here would emphasize that splitting the sentence requires O, N, time, and checking prefixes is O, 1, per word, leading to an overall time complexity of O, N. Lastly, be ready to discuss edge cases, such as what happens when the search word isn't found, the sentence is empty, or special characters are included. Being thorough in addressing these scenarios can set your solution apart. This problem is also closely related to several other string manipulation challenges on LeetCode. For instance, problem number 14, longest common prefix, involves finding the longest prefix shared across all words in a list, a variation of prefix analysis at a broader scale. Problem number 139, word break, is another related challenge where you check if a string can be segmented into a sequence of dictionary words, making it a great test of substring and segmentation logic. Problem number 28, find the index of the first occurrence in a string, is conceptually similar but focuses on locating a substring within a string, rather than just checking prefixes. Lastly, problem number 58, length of last word, looks at extracting and analyzing words within a sentence, which shares similarities with the way we split and process words in this problem. Exploring these related problems can help you build a deeper understanding of string manipulation techniques and their diverse applications. There are also alternative approaches to solving this problem, each with its own trade-offs. One option is using regular expressions to match the search word at the start of each word in the sentence. While this can be concise, it's often slower and harder to debug compared to using Python starts with method. Another approach is to manually implement the logic of starts with. This involves comparing the characters of search word with the start of each word directly. While it avoids relying on built-in functions, it can increase code complexity and is prone to off-by-one errors, so careful handling is necessary. A more advanced solution involves using a tree, or prefix tree, to store the words in the sentence and check for prefixes. While this is a powerful data structure for repeated prefix queries, it's generally overkill for this problem due to the relatively small input size. Choosing the right approach often depends on the constraints and requirements of the specific problem or the interview scenario. Great job! We've reviewed the key approach for solving this problem.
discussed its complexity, and highlighted practical tips for tackling similar challenges. Don't forget to practice regularly to strengthen your skills. Thanks for tuning in, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!